So, today our topic is eigenvalues and eigenvectors, and the main focus of this video will be uh, that why do we need eigenvalues and eigenvectors. So, uh, we have been given this system of differential equations: y1 dash is equal to 3y1 plus 8y2, and y2 dash is equal to 7y1 plus 2y2. And we have also been given this vector y of 0 is equal to 5 and 2. So this is basically a system of differential equations and first order differential equations, because first order derivatives are involved in this particular system. And what we are interested in is the value is the are the functions y1 of t and y2 of t. So these are first order linear differential equations, system of first order linear differential equations. So we are interested in y1 of t and y2 of t. So basically, eigenvalues and eigenvectors, we need them to solve a system of differential equations. And we'll see that how do those values help us in solving this system of system of linear first order differential equations. So firstly we'll see a differential equation, not a system of differential equations, but um, uh, just a first order linear differential equation and how to solve that equation. Because the solution of this system of linear differential equations kind of resembles the solution of that of just one linear first order differential equation. So if we would have been given just this particular equation, dy over dt is equal to ay, and we had to solve just this particular differential equation, not a system. So that would have been easy, and the solution of this particular differential equation would have been y is equal to c into e raised to power at. C is a constant, and that constant is being multiplied by an exponential, and exponential is e raised to power at. So, firstly, we'll prove that the solution of this particular dy over dt is equal to ay differential equation is this particular value. So, firstly, we'll prove this. So, we have a differential equation dy over dt is equal to ay, and we have to solve this differential equation. So, for this, we'll use a technique called separating the variables. And what does that mean? This means that we'll move y to the left hand side, we'll move it to with dy, and we'll move this dt to the right hand side. So this y is being multiplied on the right hand side, it will be divided on the left hand side, and this dt is being divided over here, so it will be multiplied on the right hand side. So we are interested in the value of y. So as we are interested in the value of y, we'll take the integral uh, of this equation on both sides. And when we take the integral of this equation, so on left hand side we have integral of 1 over y with respect to y. So we know that the integral of this particular function 1 over y would be natural log of absolute of y. And as on the right hand side we're just dealing with a constant, so we'll have at as the integral for right hand side. And as we are doing definite indefinite integration, so we'll add a constant on one side, and here I have added the constant on right hand side. So as we're interested in y, so we don't need this natural log, so we'll take to cancel this natural log we need an exponential. So we take exponential on both sides. So taking exponential of both sides, and when we take exponential of both sides, left hand side becomes e raised to power natural log of absolute of y, and the right hand side becomes e raised to power at plus c. So e and natural log basically cancel out each other, the effect of each other. So we are left with absolute of y is equal to e raised to power at plus c. And according to laws of exponentials, we can basically write this as e raised to power at into e raised to power c. So we were interested in y, and here we have absolute of y, which is not really needed and which is really unnecessary here, because the right hand side e raised to power has two basically factors, e raised to power at and e raised to power c. E raised to power c is a positive number because e is 2.7818 up to so on is a positive number, uh, and it has been raised to some power and on the right hand side e raised to power c, which will be a positive number. Positive number raised to any number basically is a positive number, and we that is being multiplied with e raised to power at. So e raised to power at can't even be 0, so how can it be negative? So uh, right hand side is a positive number, so there is no need to put an absolute here, so y will be positive. So we can write y is equal to e raised to power at into e raised to power c, and e raised to power c is another constant. E is a constant, and constant raised to power raised to some constant power is a constant. So this basically is a constant e raised to power c, and a constant into e raised to power at will be the solution of our differential equation. Y is equal to c into e raised to power at. But the problem which we are facing here is that we have a system of linear first order differential equations. We don't have just a single linear differential equation. When we if we had a a single linear first order differential equation like this, a constant multiplied by the unknown on right hand side, then the solution would be which I explained. But here we have four coefficients with multiplied with uh, our unknowns y1 of t and y2 of t. And so basically a coefficient matrix can be made of the coefficients of these two equations. And so this system is not like this system is uh, not exactly like this differential equation, because it has a constant multiplied by the unknown. This system has a matrix multiplied with our unknown vector, which is y of t, and it has two components, y1 of t and y2 of t, because we are interested in y1 of t and y2 of t. So so uh, here we have dy over dt is equal to capital A into y. Y is basically the vector of unknowns, y1 of t and y2 of t, and capital A is basically a matrix of coefficients of the given system of differential equations. So in this case, the solution would not be exactly like when we if we had a single differential equation. It would be like y of t is equal to c into e raised to power capital A into t into x. And what is this capital X? It is a vector basically, which has been multiplied to make the right hand side a vector, because the left hand side is a vector. Y of t uh, is not a single function. It is basically a vector having two functions, y1 of t and y2 of t. So in order to make the right hand side a function, we had to multiply this side by a vector. So y of t is basically a vector, y1 of t and y2 of t. And uh, the problem here is that exponential has been raised to a matrix power. Capital A is basically a matrix of the coefficients of given equations, given differential equations. So e raised to power at is basically a problem. So e raised to power at is basically equal to e raised to power lambda t. E raised to power at, we are raising exponential to a matrix power, and we can do it using the series of e, and we know that the series of e is uh, 1 plus x plus x square over 2 factorial plus x cube over 3 factorial up to so on. When we do that here, we get e raised to power lambda t, and there's some complex mathematics involved there. So the result is basically when we take exponential of a matrix multiplied by t, we get e raised to power lambda t, and lambda is basically a constant, and we call this constant eigenvalue. And the solution, we know that solution was y of t is equal to c into e raised to power at into capital X, and y of t is equal to e raised to power at is equal to e raised to power lambda t. And mm, uh, I haven't yet understood this part. E raised to power at is equal to e raised to power lambda t, that how this e raised to power at translates to e raised to power lambda t. But uh, the basic idea remains the same, that we take the we use the series of exponential e raised to power x series, and we use that using a matrix power. So we get e raised to power lambda t, and the solution becomes y of t is equal to c into e raised to power lambda t into x. So e raised to power at is equal to e raised to power lambda t. So the solution will be y of t is equal to c into e raised to power lambda t into x. So this will be the solution to our system, our given system of first order linear differential equations. So as this is the solution of our system of linear first order differential equations, so we can basically put this value, or this will basically this will be satisfying our differential equation. So the differential equation was dy over dt is equal to capital A into y, and we are putting the value of this y in that particular equation. So we had dy over dt, so we'll be taking the derivative of this equation. So the derivative will be c into, c is a constant, that will remain the same, and when we take the derivative of e raised to power, we are taking the derivative with respect to time. So e raised to power lambda t would have will have a derivative e raised to power lambda t, and when we then we will further take the derivative of this power. So lambda t would have a derivative lambda, so into that x, that vector x. So the right hand side was dy of dt, and the right left hand side, sorry, and the right hand side is was a into y. So a into y was c into e raised to power lambda t into x. So the equation will become c into e raised to power lambda t into lambda into x is equal to a c e into lambda t into x. So this constant can be cancelled on both sides, and we can also cancel this e raised to power lambda t on both sides, because e raised to power lambda t can't be 0. We know that from its curve. Basically e raised to power lambda t, e raised to power some value, this can't be 0, because e is a positive number, and no matter what power you take, or you raise it to any power, it'll give you a positive answer. It can never be 0. So we can cancel these e raised to power lambda t terms on both sides. So what we get is the equation which we are interested in is lambda x is equal to ax, and this is basically the fundamental equation. uh, which gives us the concept of eigenvalues and eigenvectors. Lambda here is called eigenvalue, and the x involved here is called eigenvector. And this is basically also the uh, concept of eigenvector and eigenvalue. And so now we'll try to understand what does this equation mean, ax is equal to lambda x. So what the meaning of this equation is that there's a non-zero vector. Why non-zero? Because we're not interested in zero vector, because uh, that would have no information for us. Ax is, if we take a zero vector, we are interested in non-trivial equation, a non-trivial solution of this particular equation. So what the meaning of this equation is that a non-zero vector, when multiplied when it is multiplied by a matrix, it is converted into a scalar multiple of itself. We are taking a non-zero vector here, which we are calling eigenvector, and we are multiplying it with a matrix, and it is resulting into a scalar multiple of itself, a number multiplied by that same vector, that same non-zero vector. And this is basically the concept of eigenvector. Then when it is multiplied by a matrix, a matrix is a transformation, so it basically that particular matrix transforms this non-zero vector into a scalar multiple of itself. So we can say that this matrix transforms this vector into its parallel vector, because a scalar multiplied of a scalar multiple of a vector is basically parallel to that vector. So in this particular equation, lambda can be 0, positive, or negative. When it's 0, it means that a is singular. Ax is equal to, when we put lambda is equal to 0 in this particular equation, it becomes ax is equal to 0. And so ax is equal to 0, and we are interested in x. So, and x cannot be, it can't be 0 vector, it must be non-zero vector, because we are interested in non-trivial solution. And if we are interested in non-trivial solution, and for that to happen, this particular matrix A, it must be singular. Otherwise, we won't get a non-trivial solution. And now we'll prove this. So we have imposed a condition that x must be a non-zero vector here. So we're not interested in trivial solution of this equation, and for a non-trivial solution, that this A matrix must be singular. It must be singular means it shouldn't have an inverse. Its determinant must be 0. So now we'll prove that, how can we say this, that for non-trivial solution this A must be singular and so on. So let's consider that if we have x is equal to 0, if we have x is equal to 0 and we consider A to be non-singular, that means that its inverse exists. We had a system ax is equal to 0, and we wanted to find a non-trivial solution, and we consider that A. So we are basically trying to prove that if you are interested in non-trivial solution of a system ax is equal to 0, A must be singular. So let's consider its opposite. Let's say that we have a system ax is equal to 0 and we consider A to be non-singular. Then that means that its inverse exists. It's not singular, so its determinant is not equal to 0, so its inverse exists. So that means that that means that we can write ax is equal to 0. We can write that equation as a inverse into ax is equal to a inverse into 0. So we have basically multiplied a inverse because a inverse does exist if we consider a to be non-singular. So a inverse exists, and we can multiply both sides with a inverse on the left hand side. So a inverse into A is identity matrix, and identity matrix into X, and A inverse multiplied by a zero. Zero here is not a, uh, it's a vector basically, it's a null vector. So A inverse into null vector is null vector, and identity matrix into some vector is equal to that same vector. So X is equal to null vector. So what does this tell us? This tells us that when we consider A to be non-singular, the solution would always be trivial. And we basically said that we are not interested in trivial solution. So we can't really take A to be non-singular. We have to take it as a singular matrix. Only then we would be able to uh, find a non-trivial solution. So it means that we only get trivial solution for a non-singular matrix, and we are not interested in non trivial solution. So we must consider A to be singular. So we have seen the case of lambda is equal to 0. So now we'll be taking lambda, negative lambda and positive lambda. And for negative lambda, let's consider lambda to be negative 1. So the equation will become ax is equal to minus 1 into x. So what does this tell us? This tells us that we have a vector x, and when we multiply that particular non-zero vector with matrix A, or we transform this matrix, this vector using this matrix A transformation, we get negative 1 into that same non-zero vector. So ax is basically negative x, and negative x is the opposite direction of x, so it will be in this direction. So this will be our diagram, and this will be our eigenvector x, and this will be our eigenvalue minus 1. So lambda can be minus 1, and this will be the case. This will be the diagram for that. If minus 1 is the eigenvalue and x is an eigenvector, this will be the diagram. If we consider positive lambda, we consider lambda to be in between 0 and 1. It is not equal to 1, it is not equal to 0, it's in between those two values. So we have so it's basically greater than 0 and less than 1. So when we have a vector x in this direction, and lambda is basically 0 point something, it's in between 0 and 1. So ax is equal to some 0 point something value into x. So that means that ax is shorter in length as compared to x, but it has same direction. So ax will be shorter than this capital X vector. So ax will be shorter, and so this will be our ax. Now we take the case where lambda is greater than 1. So this means that lambda is greater than 1, which will be 1 point something or some value greater than 1. So ax is equal to 2 times x. So x was this, our vector was this, and ax is greater than or is longer in length as compared to this x vector. So the whole point of this is that lambda can be negative, it can be 0, it can be uh, greater than, it can be positive. The whole concept is that eigenvector is a vector, is a non-zero vector that when it's multiplied with a matrix, it is converted, or it is transformed into a scalar multiple of itself. It is transformed into a parallel vector of itself. Here, ax is parallel to this x. Here, ax is parallel to this x. Here also, ax is parallel to this x. So, our solution is y of t is equal to c into e raised to power lambda t into x. So, we need three things here. We need the value of this constant, we need the value of this lambda, and we need the value of this x, or the eigen value of this eigenvector and eigenvalue and this particular constant, to get what we are interested in, which is the vector y of t, which is which has two elements, y1 of t and y2 of t, and we are interested in those two functions. So we need to find the eigenvectors of the given coefficient matrix and the eigenvalues associated with those vectors. So now we'll take a look at a standard method, at the standard method of finding this eigenvector x and this eigenvalue lambda. So we have an equation ax is equal to lambda x, and a is our given coefficient matrix, and x and lambda are unknown. And we obviously, as I have discussed, that we need those two values, the value of that eigenvector and the value of that eigenvalue, in order to find the solution of our given system of differential equations. So we can move this lambda x to the left hand side. We can write it as ax minus lambda x is equal to null vector. We can take x vector common of these two values. So we'll get x into a minus lambda I. We need to write I here because something is being multiplied, something is being subtracted from this a. A is a vector and lambda is a scalar, so we can't subtract a scalar from a vector. We need to make this scalar a vector, so we'll multiply it with an identity matrix. So we'll have x into a minus lambda I is equal to 0, and we are basically interested in non-zero x. We are not interested in 0x, which means that we are interested in non-trivial solution of non-trivial solution of this equation, and so we are interested in non-zero eigenvector and not zero eigenvector. So we have to, as we saw in the case of ax is equal to 0, that there a was, we had to take that a as a singular matrix. So here we have a similar situation where here we have a minus lambda I into x is equal to 0, and we are interested in x, non-trivial x. So we have to take this particular matrix a minus lambda I to be, we have to consider this to be a singular matrix. So as we are not interested in non-zero x, so a minus lambda I will be singular. So if this is singular, if this must be singular, then its determinant is 0. So a minus lambda I is equal to 0. And the system which we were given, its coefficient matrix is 3, 8, 7, and 2. And as we have seen that a minus lambda I has 0 determinant. So we'll firstly find a minus lambda I. A is 3, 8, 7, 2 minus lambda into I. I is an identity matrix, so 1, 0, 0, and 1. And we'll simply multiply this lambda with this matrix. We'll get lambda 0, 0, lambda. We'll simply multiply all the entries by this lambda, and we get 3872 minus lambda 0 0 lambda. And as we're interested in a minus lambda I, we'll just subtract these two matrices. We'll get a minus lambda I is equal to 3 minus lambda 8 7 into 2 minus lambda, and we'll take the determinant of this a minus lambda I and put it equal to 0 to get eigenvalues. So we'll take the determinant of this matrix and equate it with 0. So we have 3 minus lambda 8 7 2 minus lambda equal to 0. And we can take the determinant. uh, it will be the multiplication of the elements on main diagonal, 3 minus lambda into 2 minus lambda, and minus the product of the elements on the secondary diagonal, 8 and 7. So we can just multiply these two uh, factors. So we'll get 3 into 2 is 6, 3 into minus lambda is minus 3 lambda, minus lambda into 2 is minus 2 lambda, minus lambda into minus lambda is plus lambda square, minus 8 into 7 is minus 56. And when we solve this equation, we have just lambda square here, and the two like terms minus 3 lambda minus 2 lambda basically give minus 5 lambda, and minus 56 and plus 6, so when they are solved there, they give us minus 50. So this is our characteristic equation, and a characteristic equation is basically a polynomial equation which has lambda as a variable, and we solve that equation to get the values of lambda, or to get the eigenvalues. So when we solve that equation, if we use factorization to solve this particular characteristic equation, we can write it as lambda square minus 10 lambda plus 5 lambda minus 50, because uh, we had to get minus 50 and minus 5. We had to get minus 5 after solving those two terms which we get here, and we had to get minus 50 lambda square as a product. So we can write lambda square minus 10 lambda plus 5 lambda minus 50 is equal to 0 after breaking the middle term. And when we take common from first two terms, we get lambda into lambda minus 10, and when we take 5 common, we get the same lambda minus 10, and we can take lambda minus 10 common from both terms, and we get lambda plus 5. So lambda minus 10 into lambda plus 5 equal to 0. So we can get the values of lambda here from this equation. So the values are lambda is equal to 10 and lambda is equal to minus 5. So we have found the eigenvalues of our given matrix. So now the next phase is to find the eigenvectors corresponding to these eigenvalues, because I said that three things are needed in order to find the solution of our given system of differential equations: eigenvalues, eigenvectors, and the value of that constant c. So the first part is done, eigenvalues. Now we'll find the eigenvectors. So each eigenvalue will have an eigenvector associated with it. So firstly, we are using the eigenvalue lambda is equal to 10, and we had this equation. We have seen this equation before: a minus lambda I into x is equal to 0. So a minus lambda I for lambda is equal to 10 will become 3 minus a minus lambda I was 3 minus lambda 8 7 and 2 minus lambda. We just need to plug the value lambda is equal to 10 here. So 3 minus 10 8 7 2 minus 10. So we get a minus lambda I is equal to minus 7 8 7 minus 8. And as we had the equation a minus lambda I into x is equal to 0, so this will become a minus lambda I is minus 7 8 7 and minus 8, and x is basically the eigenvector which we have to find here, so which is x1 and x2. it's basically a vector, and it has two components, x1 and x2, and is equal to 0, which is a null vector. So it's a vector and it has two components, 0, both of them are 0. So we have to solve this system basically, and we are interested in x1 and x2, and for that we'll use a row reduction. And what does this row reduction mean? It means that we'll write this coefficient matrix minus 7 8 7 minus 8 as it is, and we'll attach these zeros, this right hand side of zeros, with this coefficient matrix, and we'll put a line in between these two. So we'll add row 2 to row 1, and we'll get a changed row 1. So when we add row 2 to row 1, we get 7 plus into minus 7, which is 0, and we get minus 8 plus 8, which is 0, and 0 plus 0, which is 0. And the change was only in R1, row 1, so row 2 remains the same, which is 7 minus 8 and 0. So we here get a zero row, a row of zeros, which basically indicates that we have a free variable. And what does this free variable mean? It means that variables are free. We can assume any real number as a value for one variable, and the other variable will have its value in terms of that assumed value. When we have a row of zeros, it means that we can take any real value for one variable and use that value or substitute that value in an equation to get the value of the other variable. So let's assume x1 to be 1, and here we have the equation 7x1 minus 8x2 equal to 0. And we got that equation by multiplying this row 7 row with this column. So 7x1 minus 8x2 equal to 0. So now we are using this equation to find the value of variables, and we have supposed the value of x1 to be 1. So x1 is 1, and the equation is 7x1 minus 8x2 equal to 0. So x1 is 1, 7 into 1 minus 8x2 equal to 0, and 7 into 1 is 7, and minus 8x2, basically this term can be moved to the right hand side to find the value of x2. So 7 is equal to 8x2, and 8 is multiplied over here, and it can be divided on the left hand side. So we get the value x2 is equal to 7 by 8. So now we have the values of both the variables. X1 is 1, which was assumed because we had a row of zeros, and x2 is 7 by 8. So our eigenvector, when we take the eigenvalue to be lambda is equal to 10 in this particular problem, we get the eigenvector 1 and 7 by 8. Now we'll use the same procedure to get the eigenvector for the second eigenvalue, which is lambda equal to minus 5. So we'll just plug the value of lambda as minus 5. So we'll put lambda is equal to minus 5 in this A minus lambda I matrix. So we get A plus 5i, because lambda is equal to 5, lambda is equal to minus 5. So A plus 5i is equal to 3 minus into minus 5, 8, 7 into 2 minus into minus 5. So 3 plus 5, 8, 7, 2 plus 5. 8, 8, 7, and 7. So this is the value of A minus lambda I. And we know the equation is A minus lambda I into x is equal to null vector. So A minus lambda I is 8, 8, 7, and 7, and x is x1 and x2, and null vector has two elements as 0. So we'll repeat the same procedure. So we have this augmented matrix 887700, and we want a 0 row. So we'll do this operation, we'll do row reduction, and we'll multiply the second if we multiply the first row with 7 and the second row with 8, and we subtract those two, we get change in row 1, we get a 0 row. So 7R1 means 7 into 8, which is 56, minus 8 into R2, which is 8 into 7. So 56 minus 56 is 0. Same is the case with this. 8 into 7 into 8, which is 56, minus 8 into 7, which is 56. So 56 minus 56 is 0. So we get a row of zeros, and we get this because the change was in R1. So we have this row of zeros in uh, R1, and in second row we'll have the same row 770. So this row of zeros indicates that we have a free variable, and we can take that free variable, we can assume x1 to be 1 for our ease. We can take any real value, but for ease we take uh, 1 as our assumed value. So assuming x1 is equal to 1 and 7x1 plus 7x2 is equal to 0, this we get this equation uh, when we multiply this row 7 and 7 with this column x1 and x2. 7x1 plus 7x2 equal to 0. So we can put our assumed value x1 is equal to 1 in this equation. So 7 into 1 plus 7x2 is equal to 0. So 7 plus 7x2 equal to 0, and 7x2 equal to minus 7. When positive 7 is moved to the other side, it becomes minus 7, and when we multiply, when we take this 7 to the right hand side, we divide uh, it on the other side, so we get x2 equal to minus 1. So the eigenvector for lambda is equal to minus 5 is 1 and minus 1. So the eigenvectors are 1 and 7 by 8. This was our first eigenvector, and this was our second eigenvector, 1 and minus 1, x1 and x2. So the only thing which we need to find now is the value of c, and for that we will use the given initial condition, and the we can basically write the general solution for our system without the constants now. So y1 of t would be c1 into e raised to power lambda, which was 10, t into x1, which was 1 and 7 by 8, and y2 of t will be c2 into e raised to power minus 5, which was lambda, t into the eigenvector, which was 1 and minus 1. And we can multiply some constant with these two values, and we can add this as well. It will still satisfy our given system. But if we want to, this will be our general solution for this system. But if we want to write a particular solution, we'll have to use the initial condition to get the value of c1 and c2. And we were given an initial condition, which was the value of y1 and y2 at t is equal to 0. So we put t is equal to 0 in left hand side and also right hand side. So y1 of 0, y2 of 0 is equal to c1 into e raised to power 10 into t, which was 0. So c1 into e raised to power 10 into 0 into 1 and 7 by 8, plus c2 into e raised to power minus 5 into 0, because t was 0, into 1 and minus 1. So we get y1 of 0, y2 of 0 is equal to e raised to power 0. 10 into 0 is 0, e raised to power 0 is 1. So c1 into 1 into 1 and 7 by 8, plus c2 into 1 and minus 1. we can multiply a constant to a matrix or to a vector. So c1 will be multiplied with this one and this 7 by 8. So we'll have c1 and 7 by 8 c1, and we'll have c2 and minus c2. And as we are interested in c1 and c2, so y1 of 0 is equal to y1 of 0, y2 of 0 is equal to c1 plus c2, 7 by 8 c1 minus c2, because these two vectors were being added. So c1 plus c2 and 7 by 8 c1 minus c2. And we were given the values of y1 of 0 and y2 of 0, which were 5 and 2. So the equations will be c1 plus c2 equal to 5, and 7 by 8 c1 minus c2 is equal to 2. So these two are the equations, and we are interested in the values of c1 and c2, to get the complete particular solution for this system of linear first order differential equations. So we'll just simultaneously solve these two equations. By adding 2 and 3, we get c1 plus 7 by 8 c1 is equal to 7. And when we take the LCM, we get 8 c1 plus 7 c1 over 8 is equal to 7. And when we cross multiply, we get 8 c1 plus 7 c1 equal to 56. And by solving, we get c1 is equal to 56 by 15. So the first constant has the value of 56 or 15. And for c2, we'll use this value in 2. So when we use 2, we get c1 plus c2 equal to 5. And we put the value of c1, which is 56 or 15, in this equation, and we get c2, 5 minus 56 or 15. After taking the LCM, we get c2 equal to 19 over 15. So the final solution to this system is a sum of two exponentials, e raised to power 10t and e raised to power minus 5t. And those exponentials are multiplied with constants 56 over 15 and 19 over 15. And they are also multiplied with a vector 1 7 by 8 and 1 minus 1. So this will be the final solution, final complete particular solution for our system, for our given system of linear first order differential equations. So we have understood in this video that eigenvalues and eigenvectors are used to solve system of linear first order differential equations. So this is what they are used for.